share. Yeah. Hi everyone. I'm presenting ongoing work. I should publish on my video. Yeah. Okay, so I'm showing ongoing work related to an. Again, I'm showing ongoing work related to an ESA Sentinel-5 innovation project, which involves the development and evaluation of water isotope satellite retrieval by the University of Leicester. And in the context of this project, we want to combine satellite retrieved data with model data and also in-situ measurements of data. And in order to do that, we came to the question how representative actually are in-situ measurements of delta D for the larger scale variability of delta D. And yeah, that's what I like to show you today. Just like these are the first results, so yeah, very open for discussions. And yeah, we're looking at just one place and look at the D variability around this location in the French Alps. So yeah, let me first introduce these three data sets that we're using. First of all, we're using data from the LWAVE campaign, which took place in June 2019 in the French spectrometer was mounted on an ultralight aircraft, which you see at the top here. And we have a total of 11 vertical delta D profiles, which reach up to 3.5 kilometers high, and have a resolution of 30 seconds. So this is a very high resolution data set for one specific location. And the other two data sets, they give data on a larger scale. And the first one is a satellite retrieved product from the Thurnherr instrument. And during the LWAVE campaign, we had 8 overpasses close to a measurement site for which we also have data. This data set has a resolution of up to 7 kilometers. And just a very short word on how this retrieval is done, which is done by the University of Leicester. This is an iterative method where an a priori moisture profile is iteratively changed to best fit the measured spectra with the Thurnherr instrument. And what is then done with this final target moisture profile, this is weighted by a pressure weighting function, which is these weights depend on the concentration of water molecules in the vertical. And this gives them the final total column value of either H2O or HDO, which then can be used to calculate total column density values. And the third data set that we are using are isotope-enabled numerical weather prediction model simulations with Cosmo ISO. And we have 2 simulations each for 7 days with a space resolution of around 10 kilometers, explicit convection. And we are using F-6 initial and boundary data, which are provided by Martin Werner. We use this data in a 1-hourly output. And in order to compare now these outputs in the model simulations with the satellite retrievals, we need also to have sort of a total column value. And what we did here is now calculating a pressure weighting function from our Cosmo ISO outputs, and also taking the vertical moisture profiles from the Cosmo ISO. And this also gives them a total column value of H2O and HDO, which is then used to calculate delta D. And this is what we see here to the right, this total column delta D in Cosmo ISO. And this is also the variable I'm going to use now in the following slide for looking at the spatial representativeness of this blue dot here, which is the measurement site of the LWAVE campaign. So yeah, we want to better understand how does delta D vary around this dot, and how does this vary in time, and how can we then use this analysis to better compare and combine these different data sets. And yeah, we use now here 2 different statistical measures. On the one hand, Pearson correlation, on the other hand, a deviation from the side. And first, let's have a look at the correlation. So what we see here is the cross correlation of total column delta D in Cosmo ISO for 5-day time series. This means the columns here show the Pearson correlation coefficient for any grid point of this 5-day time series of total column delta D with the time series at our campaign site. And if we have dark red color, this means that we have a higher correlation with our campaign site. But the more we see in white, the distance from our campaign site in 100 kilometer steps, and you see the topography here in black contours. Sorry. And yeah, first of all, we see that we have a decrease in correlation if we go away from our campaign site. But we also see that this decrease isn't symmetric, but that it is strongly forced by the topography. So we have the highest correlations here in between the Alps and the Massif Central. Now, if you're looking at 5-day time series, this means that we cannot really look at the temporal variations of these high correlation hotspots for our campaign site. And therefore, we chose to just look at 2-day time series to still have enough points to make some statistical measures, but that we can have a look at the temporal evolution. But it's now the same as before. We would zoom in for 2-day time series. And if we just highlight the 0.8 contour line, we still see here this area of high correlation in the wrong value. Now, if we just now look at the 0.8 contour line, we can quite nicely see how these areas of high correlation change with time. And we see this here now for 10 different times, 10 different 2-day periods for the 2 model simulations. And we see that these areas can change quite strongly depending on the day. So for example, if we look at the yellow contour, this is the 2 days starting on the 18th of June. And during these 2 days, we had a cyclone in the North Sea. And this storm sector, which is here, this darker red area, was strongly influencing the area around our campaign site. And this also led to a very similar temporal evolution of delta D in this area, which led to this large area of high correlation. In contrast to that, we see here this red area, which was 2 days later when we had a high pressure system and quite weak pressure gradients here over the area, and also local convection going on, which meant the local precipitation and quite a patchy picture of delta D variations in the region, and therefore only very local correlations to this very small area here. So this is now looking at the correlation. If you also look now at the mean square deviation, what we see here is again 2-day time series, and we only see the 10 per minute contour of the mean square deviations of any grid point with our campaign site. And so all the filled areas here are areas that we have a small deviation. And we still see that we have this area here of smaller deviation, where we also had the high correlation previously. But we also see that, for example, this large yellow area disappeared, which means that these similar temporal evolutions that we saw still had quite a large absolute difference to our campaign site. Now, as a first attempt, we just combined now these 2 measures. So say we take the 0.8 contour line and this 10 per minute contour line and combine them to have a mask for each day, which gives us an idea of the area where we expect similar delta D variability as at our campaign site. So, and these masks we can now apply to our simulations and our satellite retrievals, and that's what you see here. So this is an example on the 19th of June. You see here the satellite retrievals, and here you see the Cosmo ISO simulation interpolated to the pixels of the satellite overpass. And you see here distribution. So the Cosmo ISO shows generally higher values than the satellite retrievals, which you also see here in the colors. Now, if we go closer to our campaign site, we can now apply our masks and show here now 2 different masks. First of all, just the red circle. These are the blue box plots. Means we take all pixels within this red circle, and the green distributions show only points within this red circle, but they also lie within this mask. Okay. And what we see here now is that we have, oh yeah, I forgot to tell you, this black dot here, this is the value in the Cosmo ISO simulation at our campaign site. So this is kind of the true value for our Cosmo ISO simulations. That's where we're down to go if we choose the pixels wisely. And yeah, we also see now that if we only take dots within our mask, we are much closer to this true value. And this is also mainly due to the fact that we are excluding now all of these points to the south of the Alps, which were formerly included here in the blue distribution. If we make this red circle smaller, for example, 100 kilometers, we see that distributions get narrower, but we don't really improve now how close we are to our true value. And we also see that, for example, for the spectral retrievals, we are now further off than we were with the green distribution. So if we look now at all the overpasses to obtain, first of all, we see for some of the overpasses that we have a similar behavior, for example, on the 13th of June, where we also see these green distributions fitting already quite well to the true value. But we also still see that we have some differences between the retrievals and the Cosmo simulations, which can be around 50 per minute. And this can be either due to model shortcomings, but also problems with the retrievals. So as a summary, we saw that the spatial scales of the delta D variability depend on the one hand on topography, and on the other hand, they are highly variable, they show a high variability due to the large scale dynamics. And this is something which is also useful, for example, in the planning of further campaigns, comparison campaigns, and flight campaigns, so that one should keep in mind what kind of spatial scale the campaign site has, and also in which weather situations it is best to do such flights. And just an outlook of what's further possible. First of all, we would like to apply our display analysis of the in-situ data and also increase the resolution of the Cosmo simulations, as the campaign site is in the Alps and we have quite complex topography, so high resolution simulation might improve Cosmo output. Furthermore, extend the time period to more than just these 2 weeks, and also look at further variables. And last but not least, also look at other sites. So there was LEM 2021 this summer, which took place in the Rhone Valley, with a less complex topography around the campaign site, which might give other interesting views on this method. And also, hopefully, we will get some flights from Isotopes 2022, which we also can compare to the satellite overpasses. Yeah, thank you.